Hello and welcome to Empowered Learning. This video will be about solving quadratic equations via the quadratic formula. So the first thing that we're going to do is talk about how we actually come up with this quadratic formula, what the quadratic formula communicates to us, specifically what it means by the discriminant expression inside of the quadratic formula. We'll go through a few examples that are already worked out, and then we'll do some examples on our own. So let's go ahead and get started. So the first thing that we want to note is that whenever we're talking about a quadratic equation, we are talking about an equation that has the highest exponent on any variable being a 2, such that it is in this form, okay? And so for the technique that we're going to use, we must have it in this ax squared plus bx plus c equals 0 form before we can actually use the quadratic formula. Where this actually comes from is, what I mean by that is where the actual quadratic formula comes from is by taking this particular form of a quadratic equation and doing what's called completing the square to it to kind of make it look like this. If you're unfamiliar with completing the square, that is okay. If you are in a course to where you actually need to know that, then you can check out my videos on completing the square. If you have not covered that in your course, then that's okay. It's no need to really go over it. I'm just using it in this instance to kind of give you a background on where the actual quadratic formula comes from. It is a formula, but all formulas do come from somewhere. So in short, we want to force this particular quadratic function or quadratic expression within the quadratic equation to look more like this. And so one of the advantages of making it look like that is that we can easily see, well, we can more easily see what the graph of a quadratic function looks like if it's in this form versus that form, okay? But anyway, let's go ahead and move on here. So once we have our quadratic equation in this form, all we really need to do is to identify what A, B, and C are and use it in our formula, okay? And so scrolling down here, we see that this is the actual formula that we're going to use. And so we really need to take some time to try to memorize this. And of course, if you use it a lot, you'll find out that you will end up memorizing it. So again, this is the formula: minus b plus or minus square root of b squared minus 4ac, all under the square root radical, and all of that is divided by 2a. And please make sure that when you do this, that you actually put the line, the division line, over all of it. I know that as an instructor, I have a lot of students who will write this and they'll get lazy and they'll do this part here and then they'll just do like this. And they'll forget that this part has to also be divided by 2a as well. So we don't want you to do that. So all this, that's not correct, okay? Now, within the quadratic formula, we have this expression here, the b squared minus 4ac. And this is called the discriminant. The reason that it is called the discriminant because it discriminates on what type of solutions you're going to have. And so below here, I have some descriptions of what the three cases of the discriminant is and what it tells us about the actual quadratic function that we're trying to find information about in the equation. So I'll scroll up here a little bit. So first thing, of course, it lets us know what type of solutions we have, but it also lets us know whether the actual solution to the quadratic equation, which is, put another way, you're basically trying to find out where the x-intercepts of a quadratic equation are, if it actually has any or not. Now, if your discriminant is positive, meaning that, let me scroll back down here, this number here is greater than 0, then we know that we have two real distinct solutions, okay? And so that means we'll have answers like x is equal to -1, x is equal to 5/2, so something like that. This also tells us that we actually have two places on the graph of a quadratic function where the graph actually crosses the x-axis, or put another way, it has two x-intercepts, two zeros. So that is what I am trying to show here. In the case of b squared minus 4ac equaling 0, then we have what's called a double root. And so that means we only have one solution to the quadratic equation. So in short, this simply simplifies to b squared, negative b divided by 2a. Because if we, now go ahead and scroll back up here, this part here is actually going to 0. So square root of 0 is just 0, and 0 plus or minus anything is still that plus or minus anything, okay? And so graphically what that looks like is that you have a quadratic equation just bouncing off of or touching the x-axis. And of course, this is just one example of that here, okay? Now, if b squared minus 4ac is negative, then we know that we have complex conjugate solutions. And so for those of you that are in a course where you actually study complex numbers, an example of that would be something like x is equal to 3 plus I and 3 minus I, where these two are conjugates because everything is the same except for that middle sign, okay? The plus that's right there, the minus that's right there, okay? Now, for those of you that are not studying complex numbers in your course, then you probably won't see these types of examples, but I at least want you to know that if you end up ever seeing a discriminant that is negative, then you know that you have complex conjugate solutions, and that means that the graph of your quadratic function that you're talking about has no x-intercepts or zeros. So you see how for this one, how it actually doesn't touch or cross the x-axis at any time, okay? So that is kind of the conceptual understanding behind using the quadratic formula and all the information that it gives us. From this point, we're just going to go over some examples, and simply we're just going to make sure that our quadratic formula is in this form, and then after that select what A, B, and C are and just plug in, okay? So let's go ahead and go to the next page. Now here, this is just a proof to show you how we actually get this. For those of you that aren't interested in this, you can just skip on to the next page here, but I am going to talk about this for a minute. So for the proof of this, we're basically taking our quadratic function here and we want to rewrite it like this. And so if we rewrite it like that, we know that the h here is minus b over 2a, and the k is 4ac minus b squared all over 4a, okay? And so here we're going to see that when we work this out, that's what it actually ends up being, okay? So as we go down here, if we let y equal 0, and we actually rewrite all of this, then of course it'll end up looking like this. And now what we're just trying to do is solve for x at this point, okay? So by us solving for x, of course we have to subtract k from both sides, then divide by a from this step to this step. And then from here, since we have blah or something squared equals something else, we have to take the principal root, and this is how that looks, okay? And so now from that point, just to solve for x, we add h to both sides here, and this is what we end up with. So everything is written in terms of h and k now. Now, recalling that h is the minus b over 2a, and that the k here is all of this stuff, if we go and substitute all that in and rewrite it, you can see that once we do all the algebraic manipulation, it turns out to actually be the minus b plus or minus square root of b squared minus 4ac all over 2a. Okay, and so that's how we actually get that. Now, for those of you that are wondering where does the h and the k being this expression and that expression comes from, that actually comes from us doing the completing the square method on this actual equation here. And so, and I didn't want to get too deep into that because I have other videos that explain how to do completing the square here, but if we did that, we would find this same answer here. And of course, we would just rename this part h, and we would rename this part here k. So I didn't want to, again, get too bogged down into that, but I did want you at least to know where it comes from. All right, so moving on to the next page here, we're actually going to go through some examples. So for this first example here, notice that our quadratic formula is not in the form of ax squared plus bx plus c equals 0, okay? We have to force it to be in that form before we get started. So to do that, what we need to do is subtract 2x from both sides, as well as subtract 3 from both sides of the equation, to where that simplifies to 0, and now we just have x squared minus 2x minus 3, which is equal to 0, and that's what we see here. From that point, we extrapolate what a, b, and c are. So since we have nothing here, there's an understood 1, so that's why a is 1, b is negative 2, and c is negative 3. And so then from that point, notice that I take the a, b, and c and plug it into my discriminant, which is also right here, just to see what kind of solutions I'm going to have before I start. So I calculate what the discriminant is, and I see that I end up getting 16. And so since it is a number that's greater than or equal to 0, I know I'm going to have two distinct real number solutions. So now when I go and actually use my quadratic formula, of course, I already know what b squared minus 4ac is 16. And of course, that part just simplifies to 4. When I plug in my b here, notice that this is negative b, and that b is already negative. So I do my parenthesis here to make sure that I respect the fact that b is negative, and that I also have a negative on the outside of that. So that's going to end up saying a negative times a negative is a positive. So once we're there, then the plus or minus here, if we use the plus, we get one answer. If we use the minus, we get another. And so here if we do 2 plus 4, that's 6, divided by 2 is 3. And if we do 2 minus 4, that's a negative 2, divided by 1 is a negative 1. So our solutions, or our locations where our quadratic function, x squared minus 2x minus 3, crosses or touches the x-axis, is at negative 1 and at 3. Okay. Another way that we could also interpret this is we could say, where does the graph of x squared and where does the graph of 2x plus 3 actually intersect one another? Okay. If we interpreted it that way, then we would see that at x equals negative 1 and at x equals 3, they both share the same x and y values. Okay, and so we actually use put this in quadratic form to actually make solving that a bit easier, because if we had to do it the other way, then what we would end up having to do is draw x squared like this, and then turn around and draw 2x plus 3 like that, and then here this would be 3, and that would be -1. And so, of course, it's a little bit hard to deal with it that way because then we're solely relying on the graph, whereas if we just did it via the quadratic formula, there's no graphing involved, okay? All right, let's move on to the next example. I want to make sure I get it all here. All right, so for this example, we see that this is already in the form of ax squared plus bx plus c. So all we have to do is extract out what a, b, and c are, which is 4, 2, and -3 respectively, okay? Of course, we get that from here, and from there. We calculate our discriminant again, and we see that our discriminant is greater than 0. So of course, we're going to have two real distinct solutions. One of the things that I also want to emphasize here is that if you notice 52, since we know that that's going to be the radicand here, and lost my cursor there. So it's going to be the radicand here. Notice that 52 is not a perfect square, okay? And what I mean by that is, it's not like how we had in the last problem where we had 16. Of course, 16 is a perfect square and it just ended up being 4. This is not a perfect square. So since it's not a perfect square, although we have two real distinct solutions, we also know that they're going to be irrational, meaning that they're just going to be ugly real numbers. That's how I like to put it, okay? All right, so anyway, so we get this. We know that we're going to have two real distinct solutions. We plug in the values for A, B, and C, plug in everything, and of course, we know that we're going to get 52 under here. And then from here, we take the square root of 52 and we break it down. We know that 52 is 4 times 13. So via our radical rules, we could rewrite square root of 52 as square root of 4 times square root of 13. Square root of 13 is irrational and it cannot be broken down anymore, okay? So we leave it like that. However, for square root of 4, we know that square root of 4 is a perfect square, and that would be equal to 2. So that would just simplify to 2. And so now we're here at this point. And so we notice that both of these terms in the numerator have a common factor of 2. So I factor it out here, and that just leaves me with 1 in the first term here and square root of 13 in the second term. And then from here, since we have all multiplication here, we know that this 2 and that 8 can reduce to 1/4. And so 2 goes into 2 one time, 8 goes into 2 4 times. And then of course, this is our final answer. And this is just a compact form of saying 1 plus square root of 13 over 4 and 1 minus square root of 13 over 4. And if you put that into your calculator, this first answer here is roughly 1.15, and the other one is roughly negative 0.65, or 65 100ths, okay? And again, we know that at these locations here, that will be the place where the graph of this particular quadratic function crosses the x-axis, okay? All right, so let's move on to the next example. All right, so in this case, we see that our quadratic equation is not in the form that we need it to be. So again, we have to force it to be that. And to do that, all we need to do in this instance is to add 30x to both sides, okay? Which of course makes this side 0, and then we just end up having 25x squared plus 30x plus 9 on this side, okay? From there, extract our A, B, and C. And then from that point, if we go ahead and calculate what our discriminant is, we see that in this case that we end up having 0. So what this tells us is we're only going to have one solution to the quadratic equation. And of course, that means we have a double root there, which means only one x-intercept on the graph. And so, of course, knowing that our discriminant is 0 here, we can just replace all of that with 0. Our b, of course, is 30, and our a is 25. And once we work all that out, we'll see here that how we get from here to here is that we know that 30 and 2 both have a common factor of 2. So 2 goes into 2 once, 2 goes into 30 15 times. So we have a negative 15 divided by 25. And of course, from here, both of these have a factor of 5. So 15 goes in, 5 goes into 15 3 times, 5 goes into 25 5 times. And we see that our answer is a negative 3/5. And so graphically, that just means that our graph of our quadratic equation here, our quadratic function rather, right here, only bounces off of the x-axis at x equals negative 3/5. Okay. All right, so let's look at our next example. All right, so for this next example, this will be a case where we actually see that we end up having complex conjugate solutions. If you're not studying this in your course, then you may want to skip this example and go on to the next. But if you're interested in actually seeing how everything works out here and have me explaining it, then I'll go ahead and do so. All right, so for this one, we see that our quadratic formula is in the form that we need to, or quadratic equation is in the form that we need to have it in order to extract out what A, B, and C are directly. Okay, so of course we plug in everything into the discriminant. We know B is 6, A is 5, and C is 9. So we plug all that in, and we see that we end up getting a negative number there. Okay. So since the discriminant is negative, we know that that's going to end up being a situation where we have two complex conjugate solutions. Okay, so we go ahead and plug everything into the quadratic formula. And so once we're here, of course, we get negative 6 plus or minus square root of a negative 144 divided by 10. And so for this part, I tell you to review how to change the square root by basically going to complex numbers. I'm just going to go ahead and show you how we do that here, just in case you forgot. So anytime we deal with negative square roots, we could rewrite this as negative square root of negative 1 divided by square root of positive 44. And so from here, we know by definition from complex numbers, square root of negative 1 is defined as I. And of course, we know that square root of 144 is 12. So we end up with 12i as our answer here. So that's how we end up getting that particular term in the numerator. So from that point, we see that both terms in the numerator have a common factor of 6. So we factor that out, and we just have a negative 1 in the first term and 2i left in the second term. And of course, from this point, we see that both 6 and 10 have a common factor of 2. So 2 goes into 6 3 times, and 2 goes into 10 5 times. So that's how we see the 3/5 there. And then from that point, all we just do is distribute the 3 back in, and then to put this in proper complex number form, we need to have it in what's called A plus or minus BI form, where A and B are real numbers. So that's why I'm taking this and separating it as 2 different fractions here. Okay. All right, so let's move on to some examples that we can work. All right, so for this example here, we see that we don't have this in the form that we need to be able to extract out A, B, and C, but we know that can happen if we can add 18x to both sides as well as add 2 to both sides, okay? And in doing that, of course, all that goes to 0 here, and we just end up with 3x squared plus 18x plus 2 is equal to 0. And of course, from there, we know that our A is 3, our B is 18, and our C is 2. So from there, we can go ahead and calculate our discriminant right quick to see what type solutions we're going to have. So we have 18 squared minus 4 times A times C. All right, so 18 squared is 324 minus 4 times 3 is 12. 12 times 2 is 24. So we end up with 300 here. So now using our quadratic formula, and of course this 1 and 2 here means that we're expecting two different solutions. We got minus b plus or minus square root of b squared minus 4ac all over 2a. And we'll just plug in or evaluate, as we say properly, all this. So our b, of course, is 18 plus or minus. We know that our discriminant is 300 and a is 3. So from that point, we know that 300 is not a perfect square, so we're going to have to try to break this down. And so we do know that 300 is square root of 100 times square root of 3, okay? And of course, square root of 100 is just 10, and all that over 6. So continuing on over here, all right, so now we go here and we have a negative 18 plus or minus 10 times square root of 3 all over 6. And we know from 18 and 10, both of these have a common factor of 2. So we're going to go ahead and factor that out. So that would leave me with minus 9 here, plus or minus 5 times square root of 3 there. All that divided by 6. And of course, now we know that 2 over 6 is the same as 1 over 3. So 2 goes into 2 one time. 2 goes into 6 3 times. So we rewrite, have this. And so now from here, of course, if we do negative 9 divided by 3, that would just be 3 plus or minus. And if we do 5 times square root of 3 over 3, then we can just keep it just like that. And so this answer or this answer is acceptable. And of course, if we were wanting to split them up into separate answers here, then I'll go ahead and rewrite that. That would be minus 3 plus 5 times square root of 3 over 3, or minus 3 minus 5 times square root of 3 over 3. Okay. So let's move on to the second example now. So in this example, we see that we already have everything in the form that we need to extract out A, B, and C directly. So here we know that our A is going to be 1 because the understood 1 that's right there. Our B is a negative 8 and our C is 16. So if we go and calculate our discriminant, we have a negative 8 quantity squared minus 4 times AC. Negative 8 quantity squared is 64. And 4 times 1 is 4. And 4 times 16 is 64. So you see we end up with 0 here. So what this means is that we have a double root, meaning that we only have one solution to this quadratic equation. And so the graph of it is going to be such that, in this case, it's going to look something like this, where it bounces off and goes like that. So that's what we know graphically what this is going to look like. All right, so using the quadratic formula again, got a minus b plus or minus square root of b squared minus 4ac all over 2a. And, oops, didn't mean to do that. So let me erase all this stuff here. All right, so we know that our b is going to be 8, well, negative 8 rather, plus or minus. We know that our discriminant here is 0, and of course a is 1. So of course all that is just 0, and subtract, or negative times a negative is a positive. So we just end up having 8 divided by 2, which is just 4. And so that is our only solution here. All right, so moving on to our next example, we see that this equation is not in the form that we need to have it in order to use the quadratic formula. But we see that the only problem that we have is we have a negative 12x squared here. So if we add 12x squared to both sides, that side goes to 0, and then all of this on the left side just ends up being 12x squared plus 11x minus 5 is equal to 0. And of course, then from there, we can extract out what our a, b, and c are. So a is 12, b is 11, c is negative 5. So from there, we can actually use our quadratic formula. So minus b plus or minus b squared minus 4ac all over 2a. And of course, here we'll go ahead and calculate the discriminant first. Kind of make that a bit easier for us here. And so we got 11 squared minus 4a and c. Let's see if we can kind of curve this around here. So 11 squared is 121. Let's get that looking a little better. So that's 121 minus, and here notice we got a minus times a minus, which is, or a negative times a negative, which is a positive here. So that would be positive there. So we have 4 times 12, which is 48, and then we have 48 times 5, which is 240. And all that, oh, sorry, didn't mean to do that. Let's get rid of all that. And so now we just have 121 minus 240 here. And so we see that that is a negative 119. So in this instance, you see that we're going to actually have complex conjugate solutions here. And so we're going to follow that format that we did in the other example where we saw we had a complex number there. And so we're going to try to break down the negative 119 as much as we can, keeping in mind that that negative under the radical that we're going to be looking at is going to actually turn into an I whenever we break it out to be square root of negative 1 times square root of whatever, okay? So we'll go ahead and do that now. All right, so from here, we'll go ahead and plug in everything. So we'll say minus b plus or minus, and we know this is just a negative 119 divided by 2 times a, which is just 2. And for here, we know that we can break this down as square root of -1 times square root of 119. All that divided by 24, because 2 times 12 is 24. This portion here gets translated as I, and we just have -11 plus or minus square root of 19 times I all over 24. Now, if we tried to break down 119, we would quickly see that that wouldn't work for us. And so mainly because 17 times 7 is 119. So if we were to break that down in square roots, then that would be square root of 17 times square root of 7. Both square root of 17 and square root of 7 are irrational. So because of that, there's no other way that we can really break that down, and thus it doesn't really profit us to break it down, okay? So in this instance, even though we can break it down in square root of 17 times square root of 7, it really doesn't help us. So that's why we're just going to keep it as square root of 119 here, okay? And so now all we do to write out our answers is just split them up into two separate fractions here. Okay, and that example is done. So let's look at our last example. All right, so for our last example, we see that this is already in the form that we need in order to be able to use the quadratic formula directly. So we know that our A is 3, our B is a -1, and our C is -10. And of course, if we go calculate our discriminant, see that would be a -1 squared minus 4 times 3 times a -10. And of course here, the negative times the negative ends up being a positive. And of course, -1 squared is a +1. So we end up having 1 here plus 4 times 3 is 12. 12 times 10 is 120. So we end up having 121 here, okay? All right, so we see that the discriminant is 121, so that means we're going to have two real distinct solutions for our answers. So using the quadratic formula now, minus b plus or minus square root of b squared minus 4ac all over 2a. We know that our b here is a -1. We know that our discriminant is 121, and our a here is 3. So negative times a negative is a positive. We know square root of 121 is 11, and all that is divided by 6. So finish this up. We know that we have two answers here. We have 1 plus 11 divided by 6 and 1 minus 11. Got too many ones there. So 1 minus 11 divided by 6. And of course, 1 plus 11 is 12. 1 minus 11 is -10. And of course, all of this just simplifies to 2. And of course, 10 and 6 both have a common factor of 2. So 2 goes into 10 5 times, and 2 goes into 6 3 times. And so these are our two answers here. And of course, graphically, what that would look like if we were looking at this, we had a -5/3 there, and we had a 2 here. We would have a graph that kind of goes like that through both of those, where 5/3 and 2 would be our x-intercepts. Okay? And so this concludes the video about solving quadratic equations using the quadratic formula. Hope this helped you out. Take care.